we learned about a bunch of stuff. One of the things that we learned about was Lewis structures, Lewis dot structures. We ended on this slide where we were doing Lewis structures for aluminum and selenium, and I decided to expand that and we would figure out what the ionic compound that's formed with aluminum and selenium is based on those formulas. This was kind of jumping the gun a little bit, but I wanted to get us looking at something practical. So when metals bond with nonmetals, that's what kind of compound? It's an ionic compound. Metals bond with nonmetals, it's an ionic compound. In those compounds, electrons are transferred. The metals like to lose electrons, gives electrons to the nonmetal. Nonmetals like to gain electrons in reactions. The metal becomes a cation, and the nonmetal becomes an anion. Cations being positively charged, anions being negatively charged. And that attraction between positive and negative charges results in the ionic compound. This is exactly like magnets sticking together. It's exactly the same thing. In Lewis theory, we show that by moving the electron dots off of our metal structure, like we did with the aluminum and the selenium. We transfer electrons. Like the example at the end of last lecture. Since we did an example last time, I'm going to give this to you as an exercise. Please write Lewis structures for potassium and chlorine and show the electron transfer that occurs when they bond. All right, so that was some time to do some Lewis structures for potassium and chlorine. The first step for doing Lewis structures, we need to know the symbols. And so for potassium, that's going to be K. For chlorine, that's going to be Cl. Then we need to find where they are on our periodic table. So we would take a glance up at our periodic table. We find K. It's all the way over on the left side in the first column, the first group, the alkali metals. It's in group 1, aka group 1A. It has 1 valence electron. That's what the 1A part tells us. So we draw in 1 dot. 1 dot for 1 electron. Cl we find on the complete opposite side of the periodic table. It's right next to our noble gases. It's 1 spot to the left of our noble gases in group 17 or 7A. It's a halogen. That means that it has 7A, 7 valence electrons. And when they bond, the metal gives the electron to the nonmetal. And what we get from that is that potassium turns into K+. It forms a 1+ ion, like we hopefully have memorized or could figure out by looking at the periodic table. And chlorine has 1 extra electron, and so it takes on a 1 negative charge, like we also hopefully have memorized or could figure out from our periodic table. And when we're doing Lewis dot structures, we use brackets to indicate all of these electrons belong only to chlorine. This is because there's another way we can represent, there's a different type of bond that we'll be looking at later, where we can sometimes draw the dots in between. So it's important for these in-between dots to show that these electrons only belong to the chlorine. Otherwise, it looks like a different type of bond. So this positive charge and this negative charge magnet together, and that's how we get ionic compounds. So this would be the full and complete Lewis structure for potassium chloride. In that structure, the chloride ion has an octet. Remember that an octet is 8 electrons. The octet is the goal. We want every atom, every individual atom needs to have an octet, or in the case of hydrogen, lithium, beryllium, it can have a duet, where it only has 2 electrons. That's because of our 1s orbital only having one orbital, and therefore only being able to fill with 2 electrons. The potassium lost its only valence electron, and it's left with an octet, but in the previous shell. So this K, underneath those valence electrons, has core electrons. We tear away all the valence electrons, and that's like when you buy an onion at the store and you're getting ready to use it and you have to pull off the outside layer because there's a little bit of bad stuff. We pulled off the outside layer, and now we've got a beautiful brand new layer of onion underneath. And then we write the Lewis structure of the anion with brackets and the charge in the upper right-hand corner. I think I did red. So that would look like this. The brackets, showing them here in blue, and the charge in the upper right-hand corner. In this case, just a minus, indicating a 1 negative charge. If it was 2 or 3, then we would write 2 or 3 negative. We already did an example with an alkali metal and halogen, so I'm going to skip that one. It's the same one. It's the same thing. With arrows illustrate the transfer of electrons to form calcium chloride from Ca atoms and Cl atoms. So we're forming calcium chloride. We've got calcium atoms. We've got chlorine atoms. We need to first write out what we have. We've got calcium. Calcium has how many valence electrons? Yes, it has 2 valence electrons. So we'll give it 2 valence electrons. I'm going to do those on opposite sides. And a chlorine atom is going to have how many valence electrons? Yeah, it's going to have 7. And when this goes to form, when these react to form calcium chloride, calcium is going to happily donate an electron to the chlorine. Calcium is a metal. It loses electrons. Chlorine is a nonmetal. It gains electrons. That is going to result in chlorine having a full octet. So we'd be left with something like this. It's a 1 plus currently. So calcium plus. We'll have chlorine. We'll go ahead and just do the brackets in blue again. And that's going to have a 1 negative charge. So those will stick to each other. Chlorine has an octet. It's got 8 electrons around it. So chlorine is happy. Happy having air quotes. Atoms don't feel emotions. Calcium has 1 valence electron. That is not an octet. That is not an empty set, which would be an octet. And so we need to get rid of this 1 valence electron. Where can we donate that 1 valence electron? To another chlorine. If we've got 1 chlorine around, we've probably got more than 1 chlorine around. So let's pretend like we've got another chlorine around. Look at that. A nice little home for our 1 valence electron to go to. And so we would end up with these Cl's, give it brackets, and a 1 minus charge. The calcium is in the middle. It's lost 2 electrons now. It's got a 2 plus charge. It no longer has electrons represented around it. That means that we've removed the outer shell, so it's back to its core electrons. Its core electron configuration is going to be the same as that of a noble gas in the far right column, which is an octet. So it's happy. Happy. And then we've got our other chlorine. That has the same configuration, also a 1 negative charge. So based on the way that we can give away electrons from our calcium to our chlorines, this predicts a formula of CaCl2. which maybe feels a little bit silly to like use this as our method of getting the formula for that ionic compound, because we could have just swapped the charges and we would have gotten it a lot faster with less drawing. But this is showing us that it works with what we've already learned, at the very least. We could do the same thing for magnesium and nitrogen. Spoiler alert, it's the same as aluminum and selenium, so I'm going to choose to skip that. But if you really want to know what those blank slides are, you can come to tutorial on Thursday. I can also come up with new examples. It's pretty easy. So that is ionic bonds between metal and a nonmetal, because that's an ionic compound. When nonmetals bond with other nonmetals, a molecular compound results. Those are the compounds that we use prefixes mono, di, tri, tetra, etc. Molecular compounds contain covalent bonds. Valent looks an awful lot like valence. Co, like cooperative, working together, sharing. So they're sharing those valence electrons in the bonds. Electrons in covalent bonds count for both octets. So we seemingly get extra count. We can add to our total number of electrons that are counted seemingly by magic, but it's just through the power of friendship, sharing. So electrons in covalent bonds count for both octets. So let's look at what that might look like. Consider Lewis structures for hydrogen and oxygen. Hydrogen, being our firstest element, is going to be hydrogen with 1 electron. Oxygen, being our 8th element, has 6 valence electrons, 8 total electrons, 8 protons. So 6 valence electrons. If we imagine that there's another hydrogen on the other side, great, thank you so much. Forgot to put on Do Not Disturb, so I'm getting text massages. Hydrogen, 1 electron, oxygen, 6 electrons. This is a covalent compound. These electrons are shared. It counts for both of their octets. So one way that you might see this represented is with the dots directly in between. You just smush them together. Something like this. So if we're looking at the left hydrogen, it's got 2 valence electrons. Those count for the hydrogen. Hydrogen is happy with a duet with 2 because it's in 1s. It's very small. It only has access to 1s. 1s can have 2 electrons in it, so it's full. It doesn't have any p orbitals. The right hydrogen, same story. The oxygen in the middle has 2 groups that are just to itself. Oxygen's got 2 pairs that only count for oxygen, but it also gets to share those electrons that are in the bonds. So oxygen has 8 electrons. So oxygen has its octet. Both of the hydrogens have their duets because of sharing. And this version of showing the bonds as dots is why we have to put in the brackets for the ionic compounds. Otherwise, it looks like they're sharing. They are not sharing in ionic compounds. They are transferring. they only belong to the nonmetal. They don't belong to the metal. So we have to put those brackets in to make sure that our property lines are set. Questions about anything so far? Then we continue. So in that structure that we just saw, H2O, we'll draw it in again. In this structure for H2O, we've got bonding pairs. Bonding pairs are shared. Bonding pairs are bonds. So we've got two bonding pairs circled here in the purple. We also have lone pairs or non-bonding. Lone pairs are only on one atom. For both of these, they're pairs. That means that they're a set of 2 electrons. So in orange, go Tigers, we've got 2 lone pairs on our oxygen. Again, this is only one way to represent things, and this is not my favorite way to represent them, the bonds that is. Bonding pairs can also be shown as lines, which I prefer, to emphasize that they are a bonding pair. So what that would look like is this. So we've got 2 bonding pairs, 2 bonds. Each of these little lines represents 2 electrons. 1 line, 2 electrons. They're sharing. If you're going to be taking more chemistry, then I suggest you get familiar with looking at them as lines, because that's typically what people do, especially when you get to bigger compounds. They just show you lines for bonds. So for the oxygen, we've got 1, 2 bonds, and we've got 1, 2 lone pairs, total of 4 pairs. 4 pairs, that's a lot of fruit. That's all our fiber for the day. That's also 8 electrons. So oxygen is happy it's got its octet. Lewis theory also does some cool things. So you may remember that we've got some diatomic molecules. Hopefully that wasn't a surprise for you yesterday. Many people forgot, as I expected. Lewis theory explains why the halogens, group 17 or 7A, form diatomic molecules. So let's look at the Lewis structure for bromine. Bromine is Br. It's got 7 valence electrons. If we have another bromine, which is also unhappy because it only has 7 electrons and not a full octet, they can make a deal. This is like that one friend that you joked with in high school. Hey, if we're not married by 40, let's just get married and, coexist, get our tax benefits, right? This is the same sort of thing, except that bromine wants to do it now. Bromine needs its octet, right? Both of these bromines need their octet, and they say, what if we just share 1 electron? What if I let you borrow my electron, you let me borrow your electron? And so that's what they do. So bromine bonds with another bromine. So each bromine has the same configuration. We've got 3 lone pairs. And we've also got 1 bond. Each lone pair is 2 electrons, 3 times 2, 6 electrons amongst our 3 lone pairs. We also have the 1 bond that's also 2 electrons. So for those of you keeping track, how many electrons does each bromine have? valence electrons. What's 6 plus 2? 7? No, 8. 6 plus 2 is 8. Each of these bromines has a full octet. Mission accomplished. The bromines are now stable. So bromines get their octets. That's good. That's why they form diatomic molecules, because if they share, then they don't have to go steal it from something else. If you had a bromine that was just by itself, it probably would just go find anything else just about and steal an electron or bond to it. Like your DNA, it would just say, I'm with you now, DNA, and then your body would be like, why is there a bromine here? There shouldn't be a bromine here, and then like everything gets screwed up and you get cancer. Maybe. I don't know, I'm not a biologist. Lewis theory also produces hydrogen as a diatomic molecule for the same reason. Hydrogen has 1 electron. It wants to have how many electrons? Valence electrons. What's the mission? What's the goal for hydrogen? If bromine wanted 8, hydrogen wants how many? 2. Hydrogen wants 2. It wants 1s2. It wants that helium configuration. It wants to pretend like it's a noble gas. So it forms a bond with another hydrogen. And so we end up with hydrogen bonded to hydrogen. And since this bond counts for both, now the left hydrogen has a duet and the right hydrogen also has a duet. So this is like learning that board game that your friend knows how to play and you don't know how to play, that takes 4 hours to set up and then 10 hours to play. This is one of the rules of the game. These electrons count for both. 1 line, 2 electrons. So each hydrogen has a duet. They are happy. Happy in quotation marks because they're not actually happy, they're just stable. But that feels like being happy. We can also have double and triple bonds, as the header might have warned you. So atoms can share more than one electron pair to get an octet. So let's look at oxygen. Oxygen is one such case. Oxygen has the symbol O. How many valence electrons does oxygen have? 6. You may notice that I draw my dots in not the correct way. I don't draw them in singly first and then doubly second, because I know where the dots are going. You should draw them in singly first and then pair them up afterwards, unless you're very confident that you know where the dots are going. Again, it doesn't matter where the dots go. So I've drawn them in this way for a purpose, for a reason. How many electrons would this left oxygen need to get an octet? Left oxygen needs 2 electrons. How many does the right oxygen need? That's right, it also needs 2 because it's also oxygen. They both need 2. If they share 1 electron, that adds 1 to their valence count. So if we look at this left oxygen, it's got the 2 lone pairs, it's got 1 bonding pair, 3 pairs, total of 6 electrons, plus 1 extra, so it would have 7 valence electrons. 7 is not happy. However, if we share 2, we add another 1, and what we end up with is oxygen with 2 bonds to another oxygen, And now if we count them, we've got 4 electrons in lone pairs, 4 electrons in the double bond. Two lines equals 2 bonds. And we call that a double bond. So the 2 bonds from the 2 lines, 2 electrons each, 2 times 2 is 4. 2 lone pairs, 2 electrons each, 2 times 2 is 3? No, still 4. 4 plus 4, 8. We've got our full octets. So that's why our oxygen also forms diatomic molecules, because it can share 2 electrons, and that extra bonding pair counts for both of the oxygen atoms. They both get their full octets. Again, octet is the goal. Questions so far? How many lines do we think are in a triple bond? If the double bond's 2, how many is in 3? It's 3, sorry. I gave the answer away. Triple bond is going to be 3, and we'll look at that shortly. So the double bond is 2 electron pairs shared between 2 atoms. Double bonds are shorter and stronger than single bonds. The shorter part maybe doesn't necessarily make sense, but the stronger part definitely should make sense. It's like having 2 pieces of rope holding your trailer to your car or your tree to your car. 2 pieces of rope is going to be stronger than 1 piece of rope. In an oxygen molecule, the oxygen nuclei, so the cores, the centers, in that oxygen-oxygen double bond are closer together. They're 121 picometers. Picometers is smaller than nanometers. We've got meters, millimeters, micrometers or microns, nanometers, and then picometers. So very small distances that we're talking about, but they've measured it carefully somehow. At 121 picometers in a single bond, it would be 148 picometers. You can sort of think of them like if there were rubber bands. You got 2 rubber bands holding 2 things together. The nuclei are positively charged, so they're going to repel each other, but since you've got 2 rubber bands on them, that's going to pull them a little bit closer. The big takeaway, it's stronger than single bonds, and we're sharing 2 pairs of electrons. Let's consider N2. N2 is the needs of horses need oats for clear brown eyes. And the Lewis structure for nitrogen, how many valence electrons does nitrogen have? How many valence electrons? Five. So we draw 5 dots on there. I'll do it correctly this time. Look at that. 5 dots on our nitrogen for 5 valence electrons. We know that it's N2 already. So we can draw in another nitrogen. How many electrons does each of these nitrogens need to get an octet? If they have 5 and they want 8, how many do they need to get to 8 from 5? 3. We need 3 more electrons. We need 3 electrons to be an octet. These are the same thing, so they can't steal them from each other. They're nonmetals. We don't have any metals to steal from. So they're going to have to share. So let's draw in sharing between all of these electrons. And that would look like this. So we've got our nitrogen on the left, we've got our hamburger menu in the middle, we've got our nitrogen on the right. How many electrons are in these bonds? This equals, equals, equals. Total electrons. we've got 3 lines, 2 electrons each, so a total of 6 electrons. Three bonds, 2 electrons each. And since they're sharing these electrons, it counts for the left nitrogen, it also counts for the right nitrogen. They also have 2 electrons that are by themselves that only count for them. What do we call those? What do we call that solitary group of electrons? Yeah, we call those lone pairs. So each has a lone pair and the triple bond. Triple bond because it's 3 lines. And that's the most bonds between 2 atoms that we'll see in this class. You can also have 4 bonds, which would be a quadruple bond. You've got 4 lines, but we won't see those in this class. You can look at the internet if you want to see quadruple bonds. Or you can just draw it yourself. Any questions about single, double, triple bonds? If a double bond was stronger than a single bond, how do we think a triple bond compares? Is it weaker, the same, stronger? Stronger. Do we expect it to be longer, the same length, or shorter than a double bond? Shorter. Yeah, the trend continues. So a triple bond is when we share 3 pairs of electrons, and it looks like the hamburger menu. That's the official name for that type of menu icon. It's a hamburger menu. Today you learned, or you already knew. Those 3 pairs of electrons shared between 2 atoms. Triple bonds are shorter and stronger than double bonds, so they're also stronger than single bonds. This is nice. This is helpful. It explains some things. So comparing lengths, again, we're looking at picometers, those tiny, tiny units. The triple bond length is 110 picometers. In a double bond, under different circumstances, we get 124 picometers. And because nitrogen is a diatomic molecule and it has that triple bond, it's relatively unreactive. In order for it to react with something else, you would have to break the triple bond under most circumstances. So that makes it a very unreactive molecule, which is nice. It's most of the air that we're breathing. It's like 70% of the air that we breathe is nitrogen, N2. It's also convenient because if you need an inert gas, something that doesn't react, something that doesn't blow up, that doesn't react with other things, nitrogen is super easy, relatively, to just pull out of the air. So you can buy big commercial machines that just pull nitrogen, filter it out of the air, and now you've got pressurized nitrogen. They cost a lot of money, but it's relatively easy compared to other things. Another benefit of nitrogen being unreactive is that you can put it into drinks, like nitro cold brew, or Guinness is famous for having nitrogen in it, and it gives you a different bubble mouthfeel than CO2. And I think it's also the reason why nitro cold brew sells pretty well, but you wouldn't see CO2 like carbonated cold brew, because the carbonation makes acid, and then it presumably, my assumption, ruins your cold brew, ruins the flavor. So that's all extra fun stuff. So if we are writing Lewis structures, we are often not going to just have 2 atoms, and so we need some rules. So the first thing that we want to do if we're making a Lewis structure for a covalent compound is we want the correct skeletal structure for the molecule. There may be some guessing involved in this. So we may have to guess sometimes. But we have some rules about better configurations. So our skeletal structure, just like our skeletal equation, just shows us what we have. It doesn't show us all the details. It's the bare bones. So our hydrogen atoms are always going to be terminal atoms. Why are hydrogen atoms always going to be terminal atoms, meaning they're at the end? How many electrons does hydrogen need to be happy? 2 electrons. How many electrons are in one bond? Also 2. So hydrogen can only form one bond, so you can only stick it onto something. You can't stick something else onto the hydrogen. Hydrogen gets really unhappy if you stick 2 things on it. It can only handle one thing. It's a little baby of an element. It doesn't have the capacity to handle 2 things. So hydrogen is happy with one bond, so we're going to stick it on the end. It's going to be on the outside always. So it always goes on the outside. This is true for this class and most other classes. One of the other rules for how to guess is that molecules tend to be symmetrical. The left side and the right side, if you put a mirror down the middle, would look the same. The top and the bottom, if you put a mirror through it, would hopefully look the same, as much as possible. So as much mirroring as possible. The left and the right, the top and the bottom, the front and the back in some cases. We want to maximize our symmetry. That's really because it's stable, but it also looks nice. So that's setting up our skeletal structure. The second step that we're going to have is we calculate the total number of electrons. So this is another part of the game. So we figured out where all of our atoms are going. We need to figure out how many pieces do we have to put on the board to connect them all. So we're going to count up the total number of valence electrons VE. This is all of the valence electrons. We do this by counting the number of individual atoms that we have, how many valence electrons each of those have. We do a little multiplication. We do a little bit of addition. And we usually end up with an even number. The number of valence electrons is equal to the group number for the main group elements, that 1A through 8A. So for groups 1 and 2, it's just 1A and 2A, 1 and 2. For 13 through 18, you just drop the 1 in front, and it's 3A through 8A. Or remember it some other way. It's up to you. If we have ions, then electrons are negatively charged. So we add 1 electron for each negative charge, subtract 1 for each positive charge. For example, ammonium, NH4+. It has a 1 positive charge, so this means subtract 1 electron from the total. So nitrogen has 5. We've got 4 hydrogens, which each have 1, so 5 plus 4, that's a total of 9. Then we would subtract 1 because of the positive charge, and so we would have 8 electrons, looking at my left hand only, we'd have 8 electrons to place instead of the 9 that we expected. So that's step 2. That's our VEs, our valence electrons, our total number of electrons. Then we want to distribute our electrons. We want to give octets or duets to as many atoms as possible, whatever will make them happy. To start, we're going to place bonding electrons. If it's going to be a molecular compound, all of the atoms have to be connected. So we need to have at least one bond between every pair of atoms. So all of our hydrogens are going to have one bond, otherwise they wouldn't be connected. And all of the other things, like if we've got carbon and oxygen, those would get one bond between them. And that's our minimum number of bonding electrons, which I represent as BE. That's how you'll see it on the worksheet that we're working on tomorrow. Then we distribute the remaining electrons. Remaining electrons is RE. And the general principle is that we add electrons from the outside in. Working toward the center. / central atom. Usually we'll have one central atom or 2 central atoms. So we're going to start with our outside groups, see if there's anywhere that we can add electrons in pairs to get our octets, and then if we've got any left over, then those can go on our inside electrons. We will do examples. Do we have questions so far? This also gives you some time to write, in case you're writing. All right, and then for our next step, if any of the atoms, any of the individual symbols lacks an octet, then we can form double or triple bonds to give them octets. So we can move lone pairs in to form extra bonds. With the unhappy atoms. So from something that's got an octet, or if we've just got 2 things, maybe they both contribute a little. This will not always be necessary. We won't always need double or triple bonds, but there will be many such instances, many such cases. So those are our rules. It's our general strategy for coming up with Lewis structures. This is not the last, moving up the concept ladder. This is not the last concept for the class, for this chapter. We've got another one. After we get the Lewis structure, we're going to add something else onto that. So it's important that we have all of those ideas so that we can get to those top tier ideas. Otherwise, you'll just be very confused. All right, Lewis structure for H2O. We've already seen it, but let's go through it. H2O has hydrogen and oxygen. Hydrogen has to be a terminal atom. So when we're doing our skeletal structure, the hydrogens have to be attached to the oxygen. Otherwise, they wouldn't be connected. If we attach the hydrogens to each other, they can't attach to the oxygen. It's not H2O, it's just H2, and oxygen's lonely. So we put the hydrogens flanking the oxygen. It's nice and symmetrical. The left looks the same as the right. We got a little dashed line through there. If you mirrored it, it's exactly the same. So that's our first step, relatively easy here. Our second step, we need to know how many valence electrons we have to play with. We've got one oxygen. Oxygen has how many valence electrons? 6. We've got 2 hydrogens, which each have how many valence electrons? 1. And I always do this. We'll switch it. Oxygen, 1 times 6 electrons. Hydrogen, 2 times 1 electron each. So we've got a total of 8 valence electrons to play with. We need to get everything connected for it to be a molecule. How many bonds are we going to place? We need one between the oxygen and the hydrogen. We need another between the other hydrogen and the oxygen. So that's 2 bonds. How many electrons is in 2 bonds? 4. 2 times 2. So 4 bonding electrons. So 8 total electrons, valence electrons. We subtract 4 for bonding electrons. We're left with 4 remaining electrons, and we're going to put those in to fill out our playing field, and then we'll do some checks. So our 4 remaining electrons, can we put, looking at our terminal atoms, our outside atoms, can we put any more electrons on hydrogen? We cannot. Hydrogen has its duet. It will not be happy if it goes past the duet. Can we put more electrons on our oxygen? Oxygen currently has 4 electrons because of the 2 bonds. It can handle 4 more electrons, very convenient. So we put on 2 lone pairs. 2 lone pairs, that's 4 electrons. So we've got no electrons left. All of our electrons are on the board. We already established hydrogen has its duet. Hydrogens are happy. Does oxygen have the octet that it wants? Yes, it does. It has 1, 2, 3, 4 pairs, 2 bonding, 2 lone, 2 electrons each. So we've got 8 electrons on oxygen. That's a full octet. This is a good Lewis structure. A complete Lewis structure. Questions about any of that process? This is the process that you should get in the habit of running through when you're making Lewis structures. Can also write a Lewis structure for H2CO. There are a couple of Lewis structures, a couple of skeletal structures that you might come up with. Keeping in mind that we want as much symmetry as possible, you might think that it would look like this, which would be reasonable. That's certainly one way that they could be connected. Is there a way that we can get more symmetry? Because currently we've got up-down symmetry because it's just all in a line. We don't have left-right symmetry. There is, and it looks like this. So we don't have to put everything in a line. We can have other angles as well. Usually we're just working at 90-degree angles for all of our bonds. This gives us better symmetry, left and right symmetry. We don't have that up-down symmetry, but we do have left-right symmetry, which is nice. I also know that it's this way, so that, hacks. We don't have tools to identify whether carbon's supposed to be in the middle or oxygen's supposed to be in the middle. It's carbon, so I'm just giving you the skeletal structure for that one. Then we need to count up our valence electrons. We've got oxygen, count 1. Carbon, count 1. Hydrogen, count 2. Oxygen has 6 valence electrons. Carbon has 4 valence electrons. Hydrogen has 1 valence electron each. So we've got 6 plus 4 plus 2 for a total of 12 valence electrons. You'll have a much easier time doing Lewis structures if you can quickly and easily identify how many valence electrons an element has. In order to get all of these things connected, to get them all into one cohesive unit, how many bonds do we need? Shout out where we need a bond. The options are between hydrogen and hydrogen, hydrogen and carbon, hydrogen and oxygen, oxygen and carbon. Which one of those do we need? Somebody guess. This is the structure. How do we connect it? Any guess? Between hydrogen and oxygen, carbon, or hydrogen? It's not hydrogen and oxygen. Thank you for guessing. It's not hydrogen and hydrogen. We need bonds between hydrogen and carbon, hydrogen and carbon, carbon and oxygen. What we wouldn't put in is anything like these blue lines. We would not put in those blue lines. Part of the reason for that is that if you've got a little triangle of bonds like that, that squeezes the electrons really close together, and those compounds like to explode. Those don't like to exist. This would be a little bit like if you were playing with any of those like building kits that children often have and young adults often have, and you're like trying to fit the pieces into angles that they're not supposed to be in. You have to bend them. They would like to break. It's a similar thing for our bonds. So we've got how many bonds here? 3 bonds, which is how many electrons? 6, so minus 6 bonding electrons. This is just the minimum bonding electrons. We're never going to update this. You're welcome to update it if you want to, but I'm not going to update it. So minus 6 bonding electrons. This is simply to figure out how many more electrons we have to put on the board. And the number is 6. So 6 remaining electrons. We have to put 6 more dots on this Lewis structure. Where can we put 6 more electrons? We're going to start from the outside, work our way in. Can we put more electrons on hydrogen? We cannot. It's got its one bond. It's got its duet. Let's go ahead and just mark it off. Hydrogen's happy. Don't mess with hydrogen. Oxygen is our next terminal atom. Oxygen has how many electrons currently? It has 2. It wants how many? It wants 8. 8's an octet. It wants to get up to its octet number. We've got 6 electrons. 6 electrons plus 2 electrons, that would get us up to 8. So we can put all 6 of those electrons on the oxygen. No electrons left. If we look at our oxygen, wrong tool. If we look at our oxygen, red's better. We've got our 3 lone pairs plus 1 bond. Oxygen has an octet. Which is great. Oxygen's happy. Does carbon have an octet? Carbon does not have an octet. Carbon has 3 bonds, 0 lone pairs, which is a total of 6 electrons. That is not an octet. We're too short, but not the wrapper. How do we get 2 more electrons on carbon? Who's got extra electrons that they can share with carbon? Oxygen. Oxygen has 3 lone pairs. It can put one of these lone pairs into the bond. So let's say that it's this lone pair. Put that into the bond. That would make it not a single bond, but a double bond. So then this would turn into something like this. Let's get all my colors correct. Now if we look at everything, we didn't change anything with hydrogen, right? So hydrogen still got its duets. Oxygen has how many electrons? How many valence electrons count for oxygen? 8. We've got 2 lone pairs, 2 bonds. Oxygen still has its octet. When we move lone pairs in, we don't mess up the octet of the thing we're moving them from. So the oxygen keeps its octet, but carbon gets access to 2 more electrons. So carbon has 4 bonds on it now. Carbon has 4 bonds now, which is a full octet. So the whole goal of the game is get everyone their octets, or for hydrogen, the duets. That's all we're doing with the game. Questions about coming up with that structure other than like, how would we come up with that skeletal structure? Yeah. For this class, you wouldn't be able to tell the difference between the 2 structures, so that would have been fine if you had come up with that by yourself, if oxygen and carbon were switched. Yeah. That still follows our rules for what we're learning in this class. If you take, I think it's in 1A, you'll learn more advanced versions of this, and you'll be able to tell the difference between the 2 structures. We haven't learned that. We won't learn that. It's more complicated. It's not that much more complicated, but it is. Other questions? Great. For polyatomic ions, like SO4 2-, that's a polyatomic ion, an oxyanion. NH4+. We have to pay special attention to the charge of the ion. This was in the rules, but we're bringing it up again so that we can do an example. So we're going to add 1 electron for each negative charge. We're going to subtract 1 electron for each positive charge. And the Lewis structure will be within brackets with the charge in the upper right-hand corner outside of the brackets. So it's similar to what we did with our ionic compounds for the anion, but we're doing it for the whole structure. This is so that we're saying that for this entire structure, overall, there's a positive or a negative charge. It's not specifically on any of the individual atoms. It's just overall, we've got 1 extra, 1 less, 2 extra, however many electrons more or fewer. So let's look at Cn minus, cyanide, because that's like the easiest, one of the easiest examples. So for Cn, first step, skeletal structure. This one's hard to get wrong. I would typically just write this out as C and then N. The way that I wouldn't write this is carbon in front and then nitrogen directly behind it or in front of it, because that's just super confusing and it doesn't make any sense. So as long as you don't do that, which I'm guessing none of you are even thinking about, you should be fine because it's just 2 things. You could even put them at a diagonal if you wanted to. Doesn't really matter to me, but this is how I'm going to do it. We also need the valence electrons. For carbons, we've got 1. For nitrogen, we've also got 1. How many electrons does carbon have? Valence electrons. 4 valence electrons. How many valence electrons does nitrogen have? 5. So we've got 4 electrons plus 5 electrons for a total of 9 electrons. Now here's the thing. If you do this, if you get 9 electrons and you try to place them, you will never come up with a good Lewis structure. You'll always have one that's got an octet and one that's got 7. Or you'll have one that has 9 and one that has 8. You're never going to get a nice number. What are we missing? The negative charge. What does the negative charge do for us? What does it tell us? It adds 1. Electrons have 1 negative charge. If we've got a 1 negative charge, 1 extra electron. So that's another electron. So we actually have 10 valence electrons. With 10, we can get a good number. We can get octets. How many bonds do we need to connect this thing together? The minimum number of bonds. Where do we need a bond? It's not a trick question. Where do we need a bond? Between the two. Yep. Just between the carbon and the nitrogen. We need 1 bond. 1 bond. How many electrons is that? That's right. It's 2. 2 bonding electrons. So we've got 8 remaining electrons. Now, where do we place the 8 electrons? We've got 8 left. We don't really have terminal atoms. They're kind of basically the same. Neither of them is going to fill up an octet if we distribute these evenly. That's fine. So I'm just going to give 4 to the carbon, 4 to the nitrogen. That'll distribute the rest of our electrons. So I'm going to give them as lone pairs. So minus 4 electrons on carbon, minus 4 electrons on nitrogen, 0 electrons left. All of our pieces are on the board, and now we just have to shuffle them in a way, rearrange them in a way that gives us octets. How many valence electrons count for carbon's octet? We have 6, 2 lone pairs and 1 bonding pair. Nitrogen, it's the same situation, 2 lone pairs, 1 bonding pair. They each need more, right? They don't have their octets. How can we give carbon and nitrogen more electrons? If this is all the electrons we have, how can we increase those numbers? How can we get those counts up? Huh? Another bond. That's exactly right. So we're going to move some electrons in, and let's see what this looks like. So this would look like that. Now let's check our octets again. Carbon has 1 lone pair, 2 bonding pairs. It's got 6 electrons. Nitrogen has 2 lone pairs, 2 bonding pairs. It has 8 electrons. It's happy. So nitrogen's good. Carbon is not good. Carbon needs more electrons. How do we get carbon more electrons? Another bond. Where do we get the electrons from for the bond? From the nitrogen. It has to be from the nitrogen. If we move the carbon ones in, carbon still only has the same number of electrons. So nitrogen needs to share now with carbon. So let's add this top group in. And now if we do our counts, there's 6 electrons in the triple bond. Each of them has a lone pair also. They both have their octets. This is not a correct Lewis structure. We haven't done anything wrong, but it's not a correct Lewis structure. What are we missing? It's the brackets and the charge. So in order for this to be a complete Lewis structure, it needs to have brackets and a 1 negative charge in the upper right-hand corner outside the brackets, because it's an ion. Any questions? So for ions, we have to add or subtract based on the charge. We also have to remember our brackets. And we'll take our break. All right, back from our break. Now write the Lewis structure for the ClO- ion. I'll give you 3 minutes. That was about 3 minutes. So we want a Lewis structure for ClO- ion, hypochlorite. First thing we need is a skeletal structure. Cl and O are going to be next to each other. We've got a chlorine, we've got an oxygen, we've got a negative charge. From the chlorine, we get 7 electrons. From the oxygen, we get 6 electrons. From the 1-, we get 1 electron. So we get a total of 14 valence electrons to play with. We need to connect them, so we need 1 bond, minimum 2 bonding electrons. After we place our bonding electrons, we've got 12 electrons left to place. We are going to distribute those evenly. We've got room for 6 electrons on each of our atoms. So 6 electrons on the oxygen, 6 electrons on the chlorine, no electrons left. If we count up our octets, chlorine has 3 lone pairs and 1 bond. That's 4 groups, each group being 2 electrons. 8 electrons for both of these. They're happy. And then because it's an ion, we need to add in our brackets and our 1 negative charge on the outside. And that would be our complete Lewis structure. Questions about any of those parts? There are some exceptions to the octet rule. So there's limitations to our relatively simple way of showing our bonding and figuring out bonding. It's impossible to write good Lewis structures for molecules with odd numbers of electrons because you'll end up with one having 7 and the other having 8. Just that's the way that odd electrons work. So for example, nitrogen double bonded to oxygen would look something like this. The nitrogen's got 4 electrons in the double bond, plus 2 more in the lone pair, plus 1 more, for a total of 7 electrons. The oxygen, on the other hand, because it's got 2 lone pairs, doesn't have a lone electron, has 8 electrons. It exists in nature. We cannot write a satisfactory Lewis structure for it, but it's real and it exists. Another exception to our octet rule is boron. Boron and aluminum also, because they're weird, tend to form electrons with form compounds with only 6 electrons around boron instead of the usual 8 for our octet rule. This will be important on our worksheet that we're working on tomorrow. So if you see boron, it's 6. Why? Because. Isn't that fun? There are chemists that spend their whole career studying boron and the things that boron does. I took advanced organic chemistry from one such instructor, one such professor. They were a boron chemist. Doesn't sound very exciting to me. Sounds kind of boron. Thank you. There are also some other exceptions to our octet rule. Molecules like SF6 and PCl5 have more than 8 electrons around the central atom in their Lewis structures. We refer to these as expanded octets. These are in their own section on the Lewis structure worksheet. Wrong there. Despite these couple of exceptions that we've shown you, that I've shown you, Lewis theory is still really nice, and it's effective. If you're curious why these things can have more than 8 electrons, they have empty d orbitals. Notice the row that they're in row 3. They can access the 3d. So they basically just got extra pockets they can stuff those electrons into. That's why they can break the octet rule. You don't need to know that, but that's why, in case you're wondering. There are also instances where we can have two identical, almost, Lewis structures that are both perfectly fine and good, such as with SO2. With SO2, we've got a couple of options. For our skeletal structure. Which skeletal structure do we think we're going to pick? C. I heard somebody guess. Why C? Yeah, it's symmetrical. So we're going to be using OSO here because it's symmetrical. So get rid of the rest of this stuff. So this will be our Lewis structure, skeletal structure. Oxygen has 6 electrons. So 12 electrons from our oxygens. We've got 1 sulfur that also has 6 electrons. So we've got a total of 18 electrons. To get this thing connected, we put in 2 bonds. 2 bonds is 4 electrons, 4 bonding electrons. Which gives us a total of 14 remaining electrons. Again, we're not going to do a little triangle shape here because that would explode. We're going to connect them in a line because that will not explode. So 14 remaining electrons. We can start with our terminal electrons. Each of these oxygens only has 1 bond. They've got room for 6 electrons each. So if we place 6 electrons each on 2 oxygens, that's 12 of our electrons. So 12 electrons to our O's. That's not osmium, that's O's. And then we've got 2 left over, and that will go on our sulfur. So that's all of our electrons on the board. And you might be thinking to yourself, Mr. K, that's only 1 Lewis structure. Well, we're not quite done. How many electrons do our oxygens have on them? They have 8. They've got 3 lone pairs, 1 bond, 4 groups, 2 electrons per group. That's 8 electrons. So our oxygens are good. Our sulfur, on the other hand, 2 bonds, that's 4 electrons, plus 2 more from a lone pair, that's only 6 electrons. So we need 2 more. Where can we get those 2 extra electrons from? We can't place any more. How do we get that number up? Bonds. We need to take a lone pair from oxygen and make a double bond. Which oxygen are we going to take the lone pair from? Are we going to take it from oxygen on the left in purple or oxygen on the right in orange? Go Tigers. The answer is yes. We're going to do both of those things, as it turns out. So what we are going to do is, rather than choosing, we're going to do both. So this is like that joke, if you find a fork in the road, take it. So we're going to draw 2 Lewis structures showing both options, and then we're critically, this is the important part, we're going to put a little double-headed arrow in between that says it's moving back and forth between the two of them. In reality, it's probably not actually moving back and forth between the two of them. It's something in the middle, but this is how we represent it with Lewis theory. So if you can come up with two identical, almost equally good Lewis structures, you have to draw both of them. If you can come up with 3 or 4 or 5 or 6 or 7, I can count past 7. So imagine if I did. I can, trust me. Equally good Lewis structures, you get to draw all of them and then arrows in between them. You shouldn't have to do that in this class. Usually it's just 2. Any questions about? So we call those resonance structures. So either one of those two Lewis structures for SO2 predicts that it would contain 2 different kinds of bonds, one double bond and one single bond. If we look at SO2 in nature, if you grab an SO2 molecule and you look at it under a special type of microscope, you could find that the bonds are equivalent and intermediate in strength. So they're actually like 1.5 bond. So a single and a half bond, something like that in reality. This is a little bit like if you breed 2 cats of different breeds together, you'll get something that looks like the average of the 2. So we're drawing out the 2 parent cats, and then the reality is that we've got some sort of hybrid of those 2 cats, for example. And so this is what it would look like with that double-headed arrow. We call them resonance structures. Resonance structures show up on the worksheet. Any questions? All right, write the Lewis structure for the nitrite ion, include resonance structures. Would you like time to do this by yourself? Shall we do it together? Somebody said they wanted to do it by themselves, so I'll give you a couple minutes. All right, that was a couple of minutes. So let's look at Lewis structures for the nitrite ion. We're even told helpfully to include resonance structures. So our skeletal structure, to give us some nice symmetry, is going to be, oh no, nitrogen in the middle so that it's nice and symmetrical. We've got oxygen, 2 of them, 6 electrons each, total of 12 electrons. We've got a nitrogen, 5 electrons, for a total of 5 electrons, and a 1 negative charge. For an extra electron. This gives us 18 valence electrons. To get the whole thing connected, we need 2 bonds. That's 4 electrons, which leaves us with 14 remaining electrons to place. Is anyone feeling deja vu? So we're going to distribute those 14 remaining electrons. We can put 6 on each of our oxygens. So that's minus 12 electrons to oxygens. But we've got 2 left. So we're going to put those on the nitrogen. and that's all of our electrons. And then we've got a choice to make, but not really. Electrons in from the left, in purple, electrons in from the right, in orange go Tigers. But of course, in reality, we do both. Just erase some things here. And so we've got both options now shown, and we've got our resonance structure arrow in the middle. And if this were a short answer question on an exam where you got to write it out yourself, this would not give you full points. What are we missing? Or what did we do wrong? It's got a charge. It's an ion, and so we need brackets. If you don't have the brackets and the charge, it's not complete. Now, complete resonance structures for our ion. Questions? Are we having fun with our new game? Okay, so that's resonance structures. So we've learned Lewis theory. Before Lewis theory, we had to know the number of valence electrons. We learned the number of valence electrons from electron configurations. We learned about electron configurations from quantum mechanical theory. Quantum mechanics we built out of the Bohr model. And now we're going to add one more thing on top of it. Well, two more things. So the reason that we're coming up with these shapes, one of the reasons, is so that we can predict the shape. So the diagrams, the drawings that we've been doing are not what they actually look like. In reality, they're going to, all atoms and molecules, the ones that we're drawing, they're all going to be wiggling and moving all the time a little bit. And in that wiggling, they'll end up finding the most stable configuration. So those bonds can waggle around in all three dimensions, and they're all going to move around a little bit until they find the most stable position. And the theory that we're going to use to figure out what positions they're in is valence shell electron pair repulsion theory, VSEPR theory, or VSEPR theory. Some people call it VSEPR theory, and that's not the way that the things are in order. It's VSEPR, it's VSEPR, it's not VSEPR theory. That annoys me. But we can use this to predict the shapes of molecules. So we can come up with how is everything arranged, all the electrons, and then on top of that, we can figure out how are those going to settle out, where are all the groups going to go. And this is based on the idea that electron groups, specifically valence shell electron pairs, repel each other, repulsion. So the name, the whole long name, valence shell electron pair repulsion theory, just means the electrons that are in our valence shell, the ones that we're using in our Lewis theory, repel each other. What charge does an electron have? Positive or negative? An electron. One electron. Positive or negative charge? Negative charge. How about another electron? Does it have a positive or negative charge? It also has a negative charge. So if we have electrons and they're negatively charged, are they going to want to stick together? No, they're going to want to separate. Just like negative ends of a magnet, if you get magnets together and they're not labeled positive, negative, there's a way that you can arrange them where they repel each other. That means you've got the positive or the negative poles that are next to each other. Electrons are negatively charged, they will repel each other. This whole idea is based on the idea that those electron pairs that we're drawing in our Lewis structures are going to repel each other. That's all it is. There are electron groups groups, we've got 4 things that we're going to call electron groups. Each of these counts individually as one electron group. We've got lone pairs, so like on Cl, for example, in red there, those are our lone pairs. We've got single bonds, like we see between hydrogen. That counts as one group. We've got double bonds. We've got triple bonds. A single bond counts as one group. A double bond counts as one group. A triple bond also counts as one group. And a lone pair counts as one group. So they're all clumped together. And the repulsion between the negative charges of those electrons around the central atom determines what shape they are, how they're going to spread out. Those electron groups will try to get as far away from each other as they can. It's not actually even try to, they just spread out. As much as possible. That's the entire basis for the theory. For some of you, this is going to be, hopefully for some of you, this is going to be just like super simple, cakewalk. For others of you, it's going to require memorization, a lot of hard thinking, or looking at a table. So for predicting the shapes of molecules, if we look at CO2, there's our Lewis structure. So to predict the shape of CO2, you would have to be able to draw up the Lewis structure. If we look at CO2, the central atom is carbon. Carbon has 2 double bonds on it. 1 double bond, 1 group. There are no lone pairs, there aren't any single bonds, there aren't any triple bonds. So that's 2 electron groups. They're all connected, right? The carbon's connected to the oxygens. The furthest that those 2 electron groups can get away from each other is complete opposite sides from each other. So me standing in the room right now, my hands, if those are the oxygens, the furthest that I can get them away from each other is on the opposite side of my body being the carbon. I can't get them any further away from each other, right? It's also fun because I get to T-pose on the class, assert my dominance. So CO2 has linear geometry because that's the shape, right? You could draw a line through from one hand through my chest to the other hand. So that's our linear geometry. And we're going to have a bond angle of 180 degrees, half of a circle, between those 2 points. Complete opposite sides, can't get any further away than that. Then we've got H2CO. We also saw this Lewis structure earlier, or we saw this Lewis structure earlier. We've got 3 electron groups on our central atom. Carbon, again, is our central atom. We've got 2 single bonds. And we've got 1 double bond. Each of those counts as 1 electron group. We only count for our central atom because that's the one that determines the shape. If we have 3 electron groups, the furthest that those can get away from each other gives us a trigonal planar geometry. So this is like if we're doing the YMCA dance and we're on the Y part. I got my arms up in the air, feet together. So my feet would be 1 group. Those would be maybe the oxygen. My legs each are 1 bond. That's convenient. And then my hands would be the hydrogens. So this is the furthest away they can get from each other. If I move one of my hands down, that would make a bigger gap between my hands, but then it's closer to my legs, and so those would repel each other. So after enough waggling around, the bonds would settle into approximately this shape. This is trigonal. Trigonal because we've got 3 groups. That's the tri part. Planar because it's flat. If I turn sideways, if I was Paper Mario, you wouldn't be able to see me. It'd be gone. Right. Flat, in a plane, 2 dimensions. So that's our trigonal planar geometry. And the bond angles for that are about 120 degrees. So between each of our groups, it'd be about 120 degrees. CH4, methane gas, has this Lewis structure. And this one is not square planar like it looks like, right? Because it's flat when it's on the board. We've got 4 groups on our central atom. They're all single bonds. And this is what we call tetrahedral geometry. So this would be like if we're making an X shape with our body, like we're doing jumping jacks and we started, stopped with our whatever this shape is, right? This is what it looks like on paper. Just imagine me rotate it a little bit. I'm not going to do that. This is not the furthest these groups can get away from each other because we're not trapped in 2 dimensions. We're in 3 dimensions. And so if we twist, so if you do an X and then twist, the hands can actually come a little bit further away from each other. And then because my arms and legs are not in the same plane, they can kind of shrink down a little bit. And so we get better than 90 degrees between our bonds. We get 109.5 degrees. So that's our tetrahedral geometry. This tetra meaning 4, and hedral meaning faces. So if you connected all of the hydrogens and made, filled those shapes in, this would be the same shape as a D4, a 4-sided die. Any questions about shapes so far? Okay, more shapes. How about the shape for ammonia? Ammonia has this Lewis structure. It's got 4 electron groups. This is our first time seeing lone pairs included in our electron groups. The reason that this is important is because the shape that the electrons repel each other is different than the shape of the things that take up space. So electrons, kind of funky, don't really take up space. Hydrogens having protons, nuclei are really big compared to our electrons. Our electrons, who knows where they are at any given point in time. Our hydrogens take up space. Our electrons don't really take up space. And so we've got 3 groups that take up space and 1 that doesn't, but the one that doesn't still deflects the other groups. So we've got 2 different types of geometry. We've got electron geometry. This is the shape of the electron groups. So this includes lone pairs. We have to consider this first because all of our electron groups repel each other. Then we've got our molecular geometry, the shape of the molecule. So this excludes lone pairs. So the way that I do this when I demonstrate it in class is I'll make the shape for the electron geometry for the number of groups that we've got. We've got 4 electron groups. All right, so we're going to hit our X shape and then twist 90 degrees. We've got 4 electron groups. One of them is a lone pair, so we just get rid of it and keep the rest. So you'll notice, how many groups do I have now? 2 feet, 1 hand, 3 groups. 3 is trigonal. is it in a two-dimensional plane? It's not, right? Because this lone pair group is repelling this other group out of the way. And so we've got 3 points. And so we've got actually a trigonal pyramidal shape. So it's like a pyramid with 3 legs, or a tripod shape. So it's a trigonal pyramidal shape. Because that lone pair is forcing those atoms to deflect out of the two-dimensional space. Because we got our tetrahedral, we get rid of one of the groups, and these are not in a two-dimensional plane. So pyramid shape, not planar. So we've got trigonal planar, we've got trigonal pyramidal. Trigonal planar is flat, trigonal pyramidal is not flat. Another shape that we can come up with is the shape of H2O. So to come up with the shape, the molecular shape, the molecular geometry, we count up the lone pairs, or the electron groups. We've got 4 electron groups. 2 of them are lone pairs. So since we've got 4 electron groups, we're going to hit our 4 electron group shape. We hit our shape, and now we have 2 lone pairs, so we're going to get rid of 2 pairs. What shape are my feet and torso making? It's like this sort of a thing that I'm doing with my hands, right? So it's a bent shape. It's not linear. It's bent off at an angle rather than being linear. It's also not trigonal because we don't have 3 things attached to our central atom. We've only got 2 atoms attached to our central atom. Lone pairs force the H's to bend out of a line shape. So instead of being linear, it's bent. It's not 180 degrees. So looking at an example of that with our lone pairs, here represented as these yellow groups, if we get rid of those lone pairs, this is not in a line. The oxygen in the middle, the hydrogen on the sides, is not perfectly straight 180 degrees in a line. It's bent off at an angle. There's another way that we can get a bent shape that I don't have shown here. I can't think of the example, but it would be if we start with a trigonal planar shape. So we've got 3 electron groups, and one of them is a lone pair. So imagine if my feet don't exist. I can't make that happen in class. That would be very bad. And then my hands are the 2 remaining groups, right? So trigonal planar, and then do a magician's trick to get rid of my lower half of my body. My hands are up at an angle still. They're being repelled by my feet, which are invisible. So we've got a bent shape instead of a linear shape. Bent, linear. You seeing that? That's all of the shapes that we will learn. That's all of them. There are many more shapes. There are many more complicated and fun shapes. We will not be having that fun. We will not be having that complication in this class. There's also a table. That table looks like this. There's a different version of the table that I give you on the exam usually. So we've got the number of electron groups in the central atom. We've got the number of bonding groups being single, double, or triple. And we've got the number of lone pairs. So you figure out how many electron groups you've got, how many bonding groups, how many lone pairs, and then you can come up with the electron geometry and the molecular shape. On the worksheet, you'll be asked for the shape of things. That's the molecular geometry that we want for that. So if you want to predict geometry using valence shell electron pair repulsion theory, VSEPR theory, you first need to draw a correct Lewis structure. That has 4 steps or more in and of itself. Then you figure out the number of electron groups around the central atom. That's bonds and lone pairs. Each bond, single, double, or triple, counts as one group. Then figure out how that breaks down in terms of bonding groups and lone pairs. And then you can either hit our poses, right? We've got linear, we've got our trigonal planar, we've got our tetrahedral for 2, 3, and 4 electron groups respectively. Get rid of the number of lone pairs that you have, figure out what that shape is. Remembering the names of the shape can be difficult, or you can also use the table. It's 7.7.1 in the book. It's also on the exam 3 information sheet, or it should be. Again, with the goal being get the electron groups as far away as they can from each other. Questions before we stop for the day? Okay, we are not done building on concepts. We have one more concept that we're going to stack on top of that.